Look, come on in. Don't mind the books stacked on the floor. I've been trying to organize my thoughts for the 453 seminar I'm teaching this year, and frankly, my thoughts are a bit of a mess right now. It's 2026, I'm 85 years old, and you'd think by now I'd have the answers figured out, right? But the truth is, the more we dig into the plumbing of the universe, the more we find leaks that shouldn't be there. I grew up in the South Bronx. My father was a plumber, a tough guy, and he used to tell me, "Lenny, you ain't going to be no engineer. You're going to be Einstein." Now, I don't know if I ever made it to that level, but I kept the plumber's mindset. When a plumber looks at a house where the water isn't flowing, he doesn't start by writing down a philosophical treatise on the nature of wetness. He looks for the pipe that's burst. He looks for the valve that's stuck. And right now, in the year 2026, we've found a giant leak in the very fabric of our universe. We're talking about something I call the three impossible theories. It sounds like a bad joke, doesn't it? A priest, a rabbi, and a physicist walk into a bar, and they all have a different theory about why the world exists, and they're all wrong. But in this case, the theories aren't just wrong, they're mathematically impossible according to everything we thought we knew about quantum mechanics and gravity. And yet, I'm sitting here telling you that I think all three of them are probably true. The problem starts with the kind of space we live in. We live in what's called de Sitter space. That's just a fancy way of saying the universe is expanding, and it's expanding faster and faster because of this dark energy stuff. Now, for the last 30 years, physicists have been very happy playing in a different kind of sandbox called anti-de Sitter space, or ADES. ADES is great. It's got a boundary, it's stable, and the math works out beautifully because of holography. The idea I cooked up with Gerard Hooft back in the 90s. In ADES, you can describe everything happening inside a volume by looking at the information on the surface. It's like a hologram on a credit card, but here's the catch: our universe is not ADES, it's de Sitter. And de Sitter space is a total nightmare for a physicist. It doesn't have a nice, cold boundary where you can sit and watch the show. Instead, it's got horizons. If you wait long enough, things move away from you so fast that their light can never reach you again. You're trapped in a bubble, what I call a static patch. Back in 2021, I put out this paper called Three Impossible Theories, and it was born out of a realization that we were stuck. There's this thing called the GK theorem. It basically says that you can't have a quantum theory that has both de Sitter symmetry and a finite amount of entropy. Entropy is just a measure of how much information is in a system. Our universe seems to have a finite amount of it, but the math says that shouldn't be possible if the symmetries of de Sitter space are real. It's like trying to fit a gallon of water into a thimble. It just won't go. So we're left with three choices, three theories, and each one of them is a headache. One theory says we only ever have access to our little local bubble, our static patch, and nothing else exists. That's a lonely way to live. Another theory says that de Sitter space isn't even a single thing, but an ensemble average of many different theories, a mess of different possibilities all blurred together. And the third theory says that everything we see is just a collection of matrix, degrees of freedom where everything is confined, and we're just seeing the surface of something much deeper. I've just published a new book on all of this, The Black Hole Information Paradox, because it all circles back to the same fight I had with Stephen Hawking for nearly 30 years. We fought over whether information could be destroyed in a black hole. I said no. He said yes. Eventually, he came around. But now, the stakes are higher. It's not just about one black hole anymore. It's about the whole damn universe. You see, if the universe is a hologram, where is the screen? If we're inside a bubble of de Sitter space, where is the information being stored? Is it on the horizon, the point of no return? If it is, then as the universe expands, that screen is moving away from us. It's like the plumbing of reality is constantly being redesigned while the water is still running. I want you to imagine you're a plumber, like my dad. You go into a basement and you see three pipes. Pipe A is supposed to lead to the kitchen, but it's connected to a wall. Pipe B is supposed to bring in fresh water, but it's full of sand. Pipe C is supposed to be a drain, but the water is flowing up. You'd say that's impossible. You'd say the guy who built this house was crazy. But then you turn on the faucet in the kitchen and the water comes out perfectly. That's where we are in physics right now. The math says the pipes are broken, but the universe is still running. We've spent the last couple of years, 2024, 2025, digging into something called quantum complexity to try and fix this. We're finding that maybe the impossible parts aren't bugs, they're features. We're starting to see that things like the Python's lunch, these weird geometric barriers in space-time, are actually what keep the information from leaking out in ways that would break the laws of physics. But look, I'm getting ahead of myself. Before we get into the impossible stuff, I need to tell you how I got into this mess in the first place. You can't understand where the pipes are broken unless you know how the house was built. And for me, that story starts way back in 1970 with a piece of paper, a pen, and a crazy idea about strings. Are you ready to go back to the beginning? Because if we're going to solve this de Sitter headache, we've got to start with the day I realized that particles aren't just dots. There's something much more interesting. So, we're standing in the South Bronx in my head right now, back when the air smelled like diesel and old brick, and I'm trying to make sense of why I'm at Cornell instead of fixing a leaky faucet in a basement on 174th Street. It was the late 60s. I was working under Peter Carruthers, a brilliant guy, but I had this itch I couldn't scratch. Everyone in physics back then was obsessed with these things called hadrons, particles like protons and neutrons, and they were using these incredibly complicated mathematical tools to try and figure out how they interacted. There was this guy, Gabriel Veneziano. He'd come up with this beautiful, elegant formula that seemed to describe how these particles scattered off each other. It was called the dual resonance model. It was a piece of math that worked, but nobody knew why it worked. It was like finding a blueprint for a machine, but having no idea what the machine actually looked like. I remember sitting there, looking at that formula, and I started thinking like a plumber. If you see a vibration in a pipe, you don't just look at the pressure gauge, you ask what's vibrating. I started playing with the idea that maybe these particles weren't little points of stuff at all. What if they were tiny vibrating pieces of string? I spent months on this. I realized that if you treat a particle as a little relativistic rubber band, a string, all those weird mathematical properties in Veneziano's formula just popped out. It wasn't magic, it was mechanics. Different notes played on the same string gave you different particles. One vibration is a photon, another is a graviton, another is a quark. I wrote it all down in 1970 in a paper called Structure of Hadrons Implied by Duality. I thought I'd set the world on fire. I sent it off to Physical Review, and I waited for the phone to ring. I figured the Nobel Committee was probably looking up my number, but you know what happened? Nothing. Not a damn thing. It turns out two other guys, Yoichiro Nambu and Holger Nielsen, had the same idea at roughly the same time. But even worse, the physics community just wasn't ready for it. They thought it was a mathematical curiosity, a toy. They called it string theory, but they said it with a bit of a smirk, like it was some hippie nonsense. I was a bit dejected, sure. But being a Bronx kid, you don't just quit when someone tells you your pipes are crooked. You double down. By 1974, I started working with John Kogut. We were looking at why you never see a quark by itself. You can find an electron, you can find a proton, but you can never ever pull a single quark out of a nucleus. It was a mystery called quark confinement. We realized that the force between quarks doesn't get weaker as you pull them apart. It gets stronger, like a rubber band. We called these color flux tubes. If you pull hard enough, the string snaps, and the energy from the snap just creates two new quarks at the ends. You never get one alone. We took that idea and built what's now called lattice gauge theory. We imagine space as a grid, like a screen door, and the gauge fields, the stuff that carries forces, as the wires connecting the holes. In 1975, we published the Hamiltonian formulation of this. It was a way to see the plumbing of the vacuum itself. We showed that the vacuum isn't empty. It's full of these strings of flux, and quarks are just the knots at the ends. But while I was busy with strings and lattices, I stumbled into another problem that felt even bigger. It's the question of why we're even here. I'm not being philosophical. I mean, why is there matter? In the early universe, there should have been equal amounts of matter and antimatter. They should have bumped into each other, gone poof, and left nothing but a big cloud of light. No stars, no planets, no Bronx, no plumbers. I came up with a theory for cosmological baryogenesis, a way for the universe to end up with just a little bit more matter than antimatter. I felt pretty smart about it until I found out later that a Russian guy named Andrei Sakharov had already figured it out years earlier. His work was stuck behind the Iron Curtain, and we didn't know about it in the West. It was a classic Susskind moment, discovering something world-changing only to realize the universe or a Russian genius got there first. All of this, the strings, the confinement, the early universe, it was all leading me toward a collision course. I was learning that information, geometry, and energy are all tied together in ways that are deeply counterintuitive. And then in 1981, I went to a conference in San Francisco. There was this fellow there, a brilliant guy in a wheelchair named Stephen Hawking. He got up and made a claim that sounded like a personal insult to everything I believed about how the world works. He said that if you throw a book into a black hole, the information in that book is gone. Not just hidden, not just scrambled, but destroyed, erased from the universe. Now listen to me. To a quantum physicist, saying information is destroyed is like a plumber saying that water can just vanish out of a closed pipe. It breaks the law of unitarity. It breaks the law of conservation of information. If Hawking was right, the whole house of cards of modern physics was going to fall down. I went home that night and I couldn't sleep. I was pissed off. I knew he was wrong, but I didn't know why he was wrong. That was the start of what I call the Black Hole War. It lasted 28 years. And it was that war, that long intellectual street fight, that eventually led me to the impossible theories we're talking about today. Because to beat Hawking, I had to realize something radical. I had to realize that the book you throw into the black hole is in two places at once. It's falling in, but it's also smeared across the surface of the hole. And that idea, black hole complementarity, was just the tip of the iceberg. It was the birth of the holographic principle. But before we get into the holograms and the 2D data, we have to talk about the matrix. No, not the movie, the real stuff. The M-theory stuff that showed us that the universe might just be a giant pile of Ditto brains. You still with me? Good. Because this is where the plumbing gets really complicated. Keep your wrench handy. So there I was back in the 90s trying to finish what Hawking started. I'd come up with this idea of black hole complementarity in 93 with Thorlacius and Uglum. It was a radical move. We said that if you're falling into a black hole, you see one thing, and if you're watching from the outside, you see another, and both of you are right. It sounded like a paradox, but it was the only way to keep the information from vanishing into thin air. But that led me to something even bigger, something that really changed the game. I'm talking about the holographic principle. I wrote this paper in 1994. The World as a Hologram, building on an idea from my friend Gerard Hooft. It's my most cited work, about 400 or 500 citations now, which is a lot of physicists scratching their heads over it. The idea is simple, but it's crazy. Our 3D world is just a projection of 2D data sitting on a boundary. Think about a hologram on a credit card. It looks 3D, but it's just a flat piece of plastic. We said that for every Planck area of surface, you get exactly 1 degree of freedom. That's it. That's all the bits you get to build a universe. Now, for about 25 years, this worked beautifully in a specific kind of laboratory we call anti-de Sitter space, or ADS. In ADS, the universe is like a soup can. Gravity is the soup inside, and quantum mechanics is the label on the outside. My colleague Joan Maldacena showed how this works in 1997, and we all spent decades high-fiving each other because the math was so clean. I even worked on the BFSS matrix model around that time, showing that M-theory is just a bunch of Ditto brains, basically just a giant pile of matrices. We felt like we were finally getting the plumbing of the cosmos right. But here's where the headache starts. I'm sitting here in 2026, look at the students in my early universe class PHY sys 3662, and I have to tell them the truth. We don't live in a soup can, we live in de Sitter space, and de Sitter space is a whole different beast. In de Sitter space, our universe, everything is moving away from everything else because of dark energy. If you wait long enough, galaxies will zip away so fast that their light will never reach you again. You end up in what I call a static patch. It's like being in a warm, lonely room where the walls are made of light you can't see past. That boundary, that horizon, is where the information is supposed to live. But there's a massive leak in this theory. Back in 2021, I published 3 impossible theories because I realized something was fundamentally broken. There's a mathematical no-go theorem, the GKS theorem. It says that if you have a finite amount of entropy, a finite number of bits in your bubble, you cannot have the perfect symmetry that de Sitter space demands. It's a flat-out contradiction. It's like saying you have a pipe that's exactly 10 feet long, but it also has to be infinitely long to fit the house. You can't have both. I've been debating this with guys like Nerovlansky and Verlund for years now. We're arguing about whether de Sitter space even exists as a single thing, or if it's ensemble average, a blurry mix of many different possible universes. If it's an ensemble, then there is no single real universe. That's a hard pill to swallow, even for me. Think about it like a plumber looking at a boiler. In ATS, the boiler has a nice solid pressure relief valve on the outside wall. You can measure everything from there. But in de Sitter, the valve is inside the boiler, and as the pressure builds, the valve moves further away from you. You can't get a clear reading. The hologram that's supposed to describe us is inside our own horizon, and it's expanding. This is why quantum gravity in de Sitter space seems impossible. We have these three approaches, and each one of them has a broken pipe. Theory 1 says we only exist in our local patch, but then we lose the big picture. Theory 2 says the universe is a messy average, which makes my skin crawl. And theory 3, the matrix model approach, says that almost everything is confined, that we can't even see the most basic building blocks of reality. I spent the last few years, 2023, 2024, 2025, digging into how complexity might save us. We're looking at things like complexity equals action. The idea is that the complexity of a quantum state, how hard it is to build it, is actually what creates the volume of space inside a black hole or a universe. In 2025, I put out a paper on universality in long-distance geometry, trying to show that even if the pipes look broken up close, there's a pattern to the mess that makes sense from far away. But even with complexity, the de Sitter headache won't go away. We're trying to describe a system from the inside out, but the outside keeps moving. It's the ultimate version of the black hole war. Back then, I was fighting Hawking about what happens at the edge of a hole. Now, I'm fighting the math about what happens at the edge of the entire universe. It's 2026, and I still feel like that plumber's son looking at a basement full of water. I know the water is coming from somewhere. I know there's a logic to it. But every time I think I've found the main shut-off valve, the universe shows me a new set of pipes that shouldn't even be there. Wait, don't go yet. We need to talk about the Python's lunch. If you think expanding universe is weird, wait until you hear why the geometry of space itself is trying to stop us from reading the cosmic code. It involves wormholes, entanglement, and a very hungry snake. You ready for that? Good? Let's keep going. Look, let's get into the weeds here, because this is where the story gets really wild. If you thought the impossible theories were a headache, wait until you see the plumbing we had to invent just to keep the pipes from bursting. I'm talking about a period starting around 2008 that changed everything we thought we knew about how space and time are stitched together. It started with a question about speed. Not the speed of light, but the speed of secrets. I worked with a brilliant young guy named Yasuhiro Sakino, and we came up with this idea called fast scramblers. Imagine you have a secret, maybe a phone number written on a scrap of paper, and you throw it into a black hole. How long does it take for that information to get so smeared out, so mixed up with the rest of the black hole that you can't tell it was ever there? We found out that black holes are the fastest blenders in the universe. They scramble information at a speed that's logarithmic with respect to their size. It's a fundamental limit. Nothing in nature can hide a secret faster than a black hole. But why does that matter? Well, it matters because of what happened in 2013. I was talking with Joan Maldacena, one of the smartest guys I've ever known, and we were looking at two things that seemed totally unrelated. One was entanglement, what Einstein called spooky action at a distance, or EPR. The other was wormholes, or Einstein-Rosen bridges, ER. We looked at each other and realized something that sounded like science fiction, ER to EPR. Every time you have two entangled particles, they are literally connected by a tiny, microscopic wormhole. Space isn't just a big empty room, it's a web of these bridges. If you want to know what holds the universe together, it's not just gravity, it's entanglement. General relativity and quantum mechanics, the two big giants of physics that have been swinging at each other for a century, finally found a way to shake hands. But then the firewall hit. Around 2012, some guys, Almeri, Marolf Polchinski, and Sully AMPS came out and said my idea of black hole complementarity was dead. They said that if information is preserved, then an observer falling into a black hole wouldn't just float through the horizon peacefully, like I said. They said the observer would hit a wall of fire and be incinerated instantly. That really bugged me. It felt like someone telling me that the pipes I'd spent 30 years laying were all leaking. I spent years fighting back, trying to find the mistake in their logic. And that's what led to the Python's lunch. In 2020, I worked with Adam Brown, Geoff Pennington, and some other great researchers on this idea. Think about a python that's just swallowed a big meal. There's a giant bulge in the middle of the snake. If you're trying to move something from one end of the snake to the other, that bulge, that lunch, is a massive geometric obstruction. We realize that the information in a black hole is trapped behind a similar kind of barrier in space-time. This Python's lunch is why it's so hard to decode Hawking radiation. The information is there, but it's buried behind a wall of complexity. It's not that the information is gone, it's just that the computation you'd need to perform to get it out is so impossibly difficult that, for all practical purposes, it's hidden. For a black hole that just collapsed a firewall is probably impossible because it's too simple. But for an old black hole, one that's been sitting around for billions of years, things get messy. I'm sitting here in 2026 and I'm looking at these 3 impossible theories of de Sitter space again. And I realize that the Python's lunch is everywhere. Our own cosmic horizon, the boundary of our expanding universe, is like the skin of that snake. We're trying to see what's on the other side, but the geometry of the lunch is blocking us. It's funny, you know, my dad used to tell me that a good plumber doesn't just fix the leak, he understands the pressure. In physics, pressure is what we call complexity. It's the idea that as things happen, the universe doesn't just get more disordered entropy, it gets more complicated. In 2018, Adam Brown and I even proposed a second law of quantum complexity, that complexity, just like entropy, always increases. And this is where the real, impossible part comes in. We're starting to see that gravity itself, the very force that keeps your feet on the ground and the planets in orbit, might just be a side effect of this complexity. I wrote a paper in 2020 called Complexity and Newton's Loss. I'm telling you, Newton would have had a heart attack if he'd read it. I'm arguing that the reason an apple falls from a tree is because the quantum state of the apple is trying to find a path of least complexity. It sounds nuts, I know. A plumber's son from the Bronx telling you that gravity is just a math problem that's getting harder to solve. But in 2026, this is where the data is pointing us. We even did an experiment in 2022, a holographic wormhole in a quantum computer, where we actually saw these dynamics play out in a simulation. We created a wormhole on a chip. It wasn't a real hole in space you could walk through, but the quantum information moved exactly the way EPR said it would. But look, I'm getting carried away. I can see you're starting to look at me like I've spent too much time in the Stanford sun. Let's take a breather. Because the next part is where we talk about why complexity equals action. It's the idea that the entire history of the universe, every star that ever burned, every person who ever lived, is just the universe performing a massive calculation. Now, listen. We've talked about strings, we've talked about holograms, and we've talked about these crazy wormholes connecting everything. But there's a question that's been sitting in the corner of the room like an unpaid bill, and it's about time we settled up. The question is, what is space actually made of? I don't mean the atoms or the field sitting inside space. I mean the room itself. Why does the interior of a black hole keep growing even after the hole itself has stopped getting bigger from the outside? If you look at a black hole from the outside, it settles down pretty quick. It reaches equilibrium. But if you look at the math of the inside, the Einstein-Rosen bridge, it keeps stretching and stretching for billions of years. It's like a house where the outside stays the same size, but the basement just keeps getting longer every day. For a long time, we didn't have a clue why. Then, around 2016, I was working with some brilliant younger guys, Adam Brown, Dan Roberts, and Brian Swingle. We hit on an idea that sounds like something out of a Silicon Valley pitch, but I promise you, the math is solid. We called it complexity equals action. In physics, action is a very specific, old-school term. It's a mathematical way of describing the history of a system, the work done over time. But we realized that in a holographic universe, the action of a specific region of space-time, something we call the Wheeler-DeWitt patch, is exactly proportional to the computational complexity of the quantum state on the boundary. Now, what the hell is computational complexity? Think of it like this. If you have a bunch of qubits, complexity is the minimum number of quantum gates or operations you need to build a specific state starting from scratch. It's how hard it is to compute that state. And what we found is that black holes are the fastest computers in nature. They don't just sit there, they are constantly computing their own internal states, making them more and more complex every second. As the complexity goes up, the interior volume of the black hole grows. The space inside is literally being created by the difficulty of the calculation. Space is just a manifestation of quantum complexity. I remember when we first started talking about this, people looked at us like we'd spent too much time in the sun. But then Adam and I took it even further. In 2018, we proposed the second law of quantum complexity. You've heard of the second law of thermodynamics, right? Entropy disorder always increases. If you drop a cup of coffee, it breaks and you can't unbreak it. But entropy reaches a maximum pretty fast. A cup of coffee reaches max entropy once it hits the floor and the heat dissipates. Complexity is different. Complexity keeps growing long after entropy has finished its job. A black hole might reach its maximum entropy in a fraction of a second, but its complexity will keep growing for a time that is exponential in terms of its entropy. We're talking about numbers with more zeros than there are atoms in the universe. This was the missing pipe in our understanding of black holes. It explains why the interior keeps growing, because the quantum state is still getting more complicated. And this isn't just for black holes, it's for the whole universe. This leads us back to that apple falling from the tree I mentioned earlier. In 2020, I wrote this paper, Complexity and Newton's Laws. I'm telling you, it's the most plumber thing I've ever written. I argued that gravity, the actual force pulling the apple down, is just the result of the quantum state trying to find a path that increases its complexity as fast as possible. We call it complexity momentum. The apple falls because the computation is easier if the apple is closer to the ground. It's a pressure, just like the pressure in a pipe. But here's the kicker, the part that brings us back to the impossible theories of 2026. If space is complexity and complexity always increases, then what happens in de Sitter space, our universe, where the screen is moving away from us? We've been looking at this thing we call the Python's lunch. It's a geometric barrier that shows up when complexity gets too high. It's like a kink in the hose. If the complexity grows too much, it becomes physically impossible to decode the information. The information is still there, but it's buried behind a wall of math so thick that even the universe itself can't get through it easily. I've spent the last year, 2025, working on this idea of universality in long-distance geometry. What we're finding is that even though these impossible theories seem to contradict each other, they all obey the same laws of complexity. Whether you look at the universe as a static patch or a matrix model, the complexity is the one thing that stays consistent. It's like my dad's plumbing. You might have 10 different ways to pipe a house, and some might look like a total mess, but as long as the pressure is right and the water gets to the tap, the system works. Complexity is the pressure of the universe. But I have to be honest with you. Even with all this complexity, we're still staring at a wall. There's a paradox in de Sitter space that we just can't shake. It's the debate I'm having right now with Nerovlansky and Verlinde. We're arguing about the boundary of the universe. Is it a real place where bits of data live, or is it just a mathematical trick? I'm 85 years old, and I'm still arguing about the same things I was arguing about with Hawking in 1981. The only difference is that now the black hole is the entire sky. I want to finish this by telling you what I think the next generation of plumbers needs to do. Because the job isn't finished, not by a long shot. The pipes are still leaking and the bill is coming due. Ready for the final wrap-up. Let's talk about the future and why being impossible might be the most important thing a theory can be. Look, I've been talking your ear off for a while now, and the sun is starting to set over the hills here in Palo Alto. It's 2026, and I'm looking at the same blackboards I've been staring at for years, only now they're covered in notes about complexity and de Sitter horizons, instead of just strings and quarks. People ask me all the time, Lenny, why do you keep doing this? You're 85. Why are you still worrying about whether the universe is a hologram or an ensemble average? I'll tell you why. It's because the plumbing isn't finished. We've spent this whole time talking about these three impossible theories of de Sitter space. I've shown you how each one has a broken pipe, how they all seem to violate some fundamental rule of physics we hold dear. But here is the thing I want the kids, the students in my PHYCCS 453 seminar and the young researchers watching this, to understand in the history of physics, impossible is usually just another word for, we're missing a layer. Back in 2023 and 2024, I was in a real scrap with guys like Narovlansky and Verlind over de Sitter holography. We were arguing about the SYK model, the simplified quantum system that we use to understand gravity, and whether it can really describe the universe we live in. We had different assumptions about boundary entropy and horizon area. My collaborator Adil Rahman and I even updated our thoughts on this in April 2025. It's a street fight, but it's the good kind. It's the kind of fight where even if you're wrong, you learn where the leak is. In 2025, I put out a paper with Adam Brown and a few others called Universality in Long-Distance Geometry and Quantum Complexity. The main point of that work, and the main point I want to leave you with, is that the universe might look messy and impossible when you look at the fine details, but there is a deep, universal logic that takes over when you step back. Complexity is that logic. Even if our three theories seem to clash, they all have to obey the same laws of quantum computation. They all have to respect the fact that space is just a side effect of how hard it is to scramble information. I recently finished a book for Springer called The Black Hole Information Paradox. It's a long treatment of the fight I had with Hawking and how that fight led us to where we are now. Looking back on it, I realized that the black hole war was just the opening act. The real war, the one you're going to have to fight, is the de Sitter war. It's the battle to understand how a universe with no solid boundary, no outside observer, and a finite amount of information can actually exist. If you're a young physicist today, don't be afraid of the contradictions. Don't be afraid to say, this math doesn't make sense. That's exactly where the gold is buried. If I'd listened to the people who told me string theory was a toy in 1970, I'd probably be back in the Bronx right now, maybe owning a very successful plumbing business, but I wouldn't have seen the things I've seen. The universe is a strange place. It's a place where every pair of entangled particles is connected by a hidden bridge. It's a place where black holes are the fastest computers ever built. And it's a place where our entire reality, the stars, the trees, the smell of a New York dilly, might just be a low-resolution image of data sitting on a cosmic horizon we can never reach. My father was right about one thing: I didn't become an engineer. But he was wrong about the Einstein part. Einstein hated the idea of spooky action at a distance. But I've spent my life showing that the spooky stuff is exactly what makes the world work. I'm just a guy who looks at the pipes. And right now, those pipes are telling us that reality is way more possible than we ever dreamed. So here is your job. Look at the three impossible theories. Don't try to pick the right one. Try to figure out the deeper plumbing that makes all three of them part of the same system. Look for the Python's lunch in the geometry of the vacuum. Look for the way complexity creates the push we call gravity. I'm 85 and I'm still learning. I'm still teaching. And I'm still looking for that main shut-off valve. If you find it before I do, give me a call. I'll be here at Stanford, probably arguing with Joan Maldacena or Adam Brown about something that shouldn't be possible. Physics isn't about having all the answers. It's about not being able to let go of the questions. It's about being a plumber who won't leave the basement until the water stops rising. The universe is expanding. The horizon is moving away. The complexity is growing. There's a lot of work to do. Now, if you'll excuse me, I've got a grad seminar to prepare for, and I think I finally figured out why de Sitter space has no chords. But that's a story for another day. Take care of yourselves, and keep an eye on those pipes.